Boa tarde a todos. Vamos começar aqui mais um seminário do grupo de Física de Partículas e Astroparticles da UFRN. Hoje temos um seminário da Letícia Guedes, que ela vai falar sobre o artigo Gamma Ray Lines in 15 Years of Fermilab Data, New Constraints on Higgs Portal Dark Matter. So now let's speak in English. So you can start, Letícia. And just a question, you want us to interrupt you with questions, or you rather that we ask in the end?
No, we'll decide. You can interrupt me, you can ask later.
Okay, then. So take your time.
Okay. So I'm going to present this article, as Álvaro said. So it uses the data of the Fermilab pointing to the galactic center to do research on indirect detection of dark matter. Okay, so indirect detection, for those who are undergraduates, it's good to know. The method of indirect detection of dark matter, it looks for what dark matter can produce. In this case, we are looking for gamma ray signals. So we suggest a model of two particles of dark matter producing the gamma rays, and we are looking for these gamma rays that produce a specific signal different from the background. And if we see this specific signal, we can trace back and get to the conclusion that it was produced by dark matter. So that's why it's indirect detection. Okay, so in this paper, it suggests us, it's not focusing on just suggesting a model. It's more of like an analysis. Normally, what's common to be done is look for this gamma production. There is two dark matter producing two photons. In this case, they look for this channel gamma Z as well. So it's a bit different, and it also produces a monoenergetic line, as it says, like the gamma. So it uses both of the signals, to put more constraints on the sigma V, that is the cross section of dark matter annihilation. So this graph I will talk about later, because it's basically the main result of the paper. So here it shows the energy of the channel gamma that would be exactly or approximately the mass of the dark matter, since it's a two channel, so two dark matter particles producing two gamma rays, and that's why the energy of the gamma would be equal to the mass of the dark matter. We can do something similar with the energy of the Z gamma, and would be related to the energy of the gamma as well. So yeah. So this paper proposes any model, a process with Higgs portal, which means that it's mediated by a Higgs boson. It doesn't show the process here in the paper, but it's basically a loop process. Since it's generating gamma rays, you can annihilate dark matter and produce a Higgs, and then directly gamma rays, because Higgs doesn't couple to photons. So would be two dark matter producing a Higgs, and then a loop, and then producing gamma or gamma Z. So they look for the galactic center. Here it's just describing the methods and how they get the data, what processes it's made to clean the data. And we are getting three, I'm going to put in this graph here, three regions of interest, that is this ROI, and it works with these three ones. These numbers are the angle in relation to the galactic center, and because that's what the formula is observing. That's the data that they're getting. So this is 3 degrees, 16, and 41. So they show here below. Let me see here, because the graphs up there is the sigma v versus the mass. So you can't see what they mean with the single line or double line. But here in the appendices, they show what would be the signal. This is the counts of the process, the gammas, and this is the energy. So this would be the double lines. There is 2 peaks, and this would be the single lines. Yeah, so that's what they're looking for. But they, with the 15-year data, they doesn't found anything. This graph here shows the significance versus the energy. So to be a signal that's significant would be, it needed to reach 5 sigma. So none of the signals reach 5 sigma in any region. And even if it did reach, none of the peaks are equal in the regions, like in the same value of energy. So it doesn't show anything significant. But this analysis of double line, as they say in this paper, it can be used to other type of data, and I mean you can still use this to discover something with other data and other regions as well. So here, this is the equation of the flux that is very important in indirect detection of dark matter. It's just the flux of the gamma rays that we get. This is the sigma v. That's the thing we are constraining in the main graph that I showed in the beginning, that I'll show again. This D and the E is the energy spectrum, and it guarantees that we are getting the channels that we want, because as we can see here, this is for the gamma gamma, is a delta function. So if the energy that we get is not the energy, is not equal to the energy that we are expecting, that is equal to the mass of the dark matter, we exclude this channel. We don't get the signal. And the same can be done to gamma z here as a delta function. So we just excludes everything that doesn't have the energy that we want to get. And this is the J factor, that is an astrophysical factor. And the ROI, the regions of interest, enters in here, because this depends on the astrophysical part, the density, the density of the dark matter and the solid angle. So this is where it will enter. It's the angle that we are seeing, the regions of interest. So yeah, it's basically here. This is the one of the graphs that we get. This is a sigma v versus the mass of the dark matter. I will show the one in the beginning because it's more complete. But it's the same signal, this line, this blue line here, and the red line. So this is comparing with the Fermi-LAT in 2015 and this Foster. This Foster is more constrained in a way, but they show in this paper some differences in the methods. But anyways, in the case of the double line, when it's up to bigger energies, it gives more constraints, as you can see, because in the bigger energies, when you consider the gamma gamma and the gamma z together, it gives a bit more constraints. So you can still use these constraints to other data, but in this case, they didn't found anything. they present here as well two models, but it doesn't seem to have been big importance in this case, because it's like they doesn't use or doesn't care about building a model. They just presented some well-known models here, with a Higgs mediating. So this would be with a scalar dark matter and a fermionic dark matter. But as I understood, it doesn't give much difference in this work to the goal they are aiming. And yeah, so they mentioned the galactic center excess as well. That is an excess of the gamma rays observed in the center of the galaxy. And it gives constraints on what's the maximum of the signal that we can get. So they try to obey these constraints. It says here that it gives a bit of attention, but it doesn't. It's not a real tension. Like it's in the bounds. And yeah, that's basically the idea of this work. The main idea is to get this double line signal analysis that can be used to order data. But in this case of the Fermilab, it doesn't show much, but it doesn't show like any significance. So yeah, it's basically it. So yes,
I have a
that's
question.
the end, I think.
I have a question because it wasn't very clear to me why they needed. I mean, I understand why they have to look for two different signals with the one line and the double line. But I mean, I'm a bit curious about how, if you know, of course, if you don't know, there's no problem as well.
Okay.
Of how they do this analysis, in the sense that I understand that there are three different places that you're looking, right? This ROI region of influence. And because I was thinking about for example, perhaps there could be a photon that came from a pair, and perhaps it is one of them is inside one region and the other is in the other region that you're looking for, or perhaps it's something like that. And
Yes.
I was wondering if they speak told something about this case, if they didn't consider this case, something like this.
Okay. In the case of that you mentioned, of a photon being in one region and the other in other region of interest, they doesn't mention at all. But what you said about the gamma Z, I understood that it's useful to see and to consider the double lines, because we are looking not for one signal but two, and it can means more. It can constrain more if we look for two bumps. I don't know if I'm being clear.
No, I see, because there's the relation from momental conservation, right? If you see
Yes.
two photons with the same energy, you can relate indirectly with dark matter annihilation. So yeah. And other thing that I was thinking about is, for example, you show a plot of the sigma v, right? And
Yes.
basically there isn't much difference between the two cases. So I was wondering if they kind of discussed that result, because to
Um,
me it seems very interesting, because it should be very different, right? I guess.
what in
So
here?
yes, yes.
Oh, the difference disappear in the end. That's
Uh-huh.
what you asking.
Yes, yes.
Um, I mean, they discussed a bit here. They say it's because, I mean, there is a part in here, but they doesn't discuss very deeply.
Oh, okay.
So here they say a bit why the gamma z is more constrained in upper energies. They doesn't say why they're equal in lower energies,
Mhm.
but yeah, it's related to the branching ratio of the gamma z. But to be honest, I didn't understand quite deeply here. But they say it's because of the branching ratio that's more constrained in the end with in bigger energies.
Okay.
To me, it's like what will be the most relevant channel in this case? I mean, what's the most important? Is the double line or the single line?
Uh,
In terms
what?
of strongest of the signal, for example.
Oh, it's the double line
Mhm.
because in the single line it's already made with a certain quantity of times. The main I think the main thing of this paper is to get this double line analysis, and it actually gives more constraints. In lower energies, it doesn't differ, but in bigger energies, it can give more constraints. So it's more important than the single line.
But I mean, if I, for example, what is easy to observe? A
What is
symbol,
it? What is what?
what's easy? Which one is easy to observe?
Oh,
Is
I
there
think
a discussion about it?
I think the single line it doesn't have a discussion, but I think it's the single line.
Uh,
Yeah. I think so as well because single line of photons you can see like
yes.
from everywhere.
Yes.
A double line of two photons with exactly the same energy, that's way more difficult.
Yeah.
Somehow, in this case, also you could know that the last process before the final states would be a week, right?
That was a question?
Was that
Yeah. Mhm. And this no, it was a comment, right?
Ah,
was a
okay,
comment?
okay, because
Yeah.
I'm not hearing very well. So sorry.
Yeah, this Z channel I think is very interesting because there's this Z will decay, right?
Yes.
So there are a lot of channels coming from the decay of the Z. So and that's what I find really interesting about this channel because I believe that it's very difficult to make this like this backward process. Like I see a signal there
Track
that
it back.
yeah, because this comes from the decay of a Z boson, for
But I think
example.
it's a ritual, so you have to match the mass of the Z.
Yes, that's
So
the
in
that's
this
the
case, I
issue.
think that's how they. Yeah.
But I mean, let's
I
assume.
don't know if this is related,
Uh-huh.
actually related to the questions that you have, but in the energy spectrum, it gets in the delta function, we differentiate like the energy, the specific energy that we want to get. In the case
Mhm.
of the photon, we want this energy of that is equal to the mass. In the case of the gamma z, we get this Ez that's
Yes. I mean, it's just an
the
algebraic
intrinsic mass of the z.
equation. But in terms of what we measure, it will be energy anyway. So the point is that in the case of the Z in the final state, we have a very specific, range of energy because I think it has to match the Z mass because it will be virtuals, right?
No, if it is Vito, it doesn't have to match because we just decay.
Okay, that's true.
Yeah.
Yes, I mean it will decay in the rest frame.
I mean, what I think they do in the end is that they look for signal from particles that you can trace them back to a same source and that they have the energy which is equal to another photon that they're measuring.
It's just like
I think that's what they do.
we need a vector boson, massive vector boson anyway.
I mean, it doesn't need to be a massive vector boson. It can be a scalar as well, right? I guess. You just need something that decays into other somethings that the energy matches with the energy that the photon with the photon. I guess it's something like this.
Yeah, and they doesn't consider the dark matter a boson. They just consider scalar and fermionic. But yeah, it's something decaying on Higgs, and and then generating gamma rays.
What is exactly the single line and double line is related to the one process?
The number of photons in the final state.
The number of photons, because one of the photons will have a smaller energy, and the other will have a larger energy. But in the case of a single line, it will be the same energy.
No, it's the opposite.
It's the opposite.
Yeah, when there are double lines, they both have the same energy. Yes.
Really?
This is from kinematics. Yeah.
Double lines in what?
Photons, 2 photons. So you look at the galactic center, and then you look for photons that you're measuring in your telescope that have this exact same energy. If you see some signal like that, then perhaps you have a signal of dark matter annihilation, for example.
Because they came from the same process.
I don't know if I understand what you're saying. Sorry, because you're saying, like, as what I understood is that the double line, the second peak would be represented by the gamma z. So the gamma that comes from the decaying gamma z. So the one peak would be of the 2 photons that are the same energy. So that's one peak, and there is 2 because there's this different energy gammas that are coming from
Yes.
the z, and I mean it's a different energy, but it's also a peak because there is also a defined energy.
Yeah, that's what I mean.
Mm-hmm.
We have the first peak is from the
Oh, I
photons
see.
of the Z process.
Yeah.
And the
You're right.
second peak is from the
Now
2 photons in the final state.
Yeah, I was thinking that you're talking about something else. Yes.
It's just because the energy divided by 2.
Exactly.
So one of the energies of the outcome.
Yeah.
So
So
because the energy there in the x-axis is the photon, the double energy of the photon.
yes.
So there is no z component.
You can see the energy of this.
Yeah.
Just
So the one of the photons will be energy in this case, which is from the z process.
Yeah.
this graph is where it came from. Like it's, I think it's centered on
The center of the galaxy.
Yeah, the galactic center.
So there is this 2 peaks. So okay, so this 2 peaks is not
Different processes.
no, there are different processes, but they don't have the gamma to be as colored.
Yeah, because
They are just-
this plot just shows the number of photons that you are seeing within this range of energy. So you're seeing a little bump, but it's not enough
Yeah, you can't
to
do
say that, well, we see dark matter annihilation. But it's interesting nonetheless, because this excess in the galactic center it's actually pretty old. I think it's 2012 or something like that. 2012. It was first discovered in 2012. And up till now, there hasn't been another way to explain this excess besides dark matter.
No,
So
there is actually one thing. It's like
the pulses, millisecond pulses. Yeah.
yes, but yeah,
Even this one is a bit tricky.
yeah.
Cannot explain exactly the excess.
Mhm.
I mean, perhaps we are seeing a signal, but there's not enough statistics yet.
Yeah.
It's really nice, really nice. Further questions? No. So, I guess that's it. Thank you a lot, Leticia. Oh, you have a question?
I mean,
Ah,
just to know if the guys, this is the first time he's here.
oh, is it?
So
Nice.
it's like to understand what's going on, what we are talking about. First, can you understand in English? Então, vou falar em português, que fica melhor. Porque só para você entender qual é a discussão, né? Porque sem contexto fica mais difícil de entender. Mas, basicamente, o que a gente está discutindo é a questão de detecção indireta de matéria escura. Então, a gente tem um centro galáctico, por exemplo, e a gente sabe que a matéria escura ela interage gravitacionalmente, então ela está em alguns objetos astrofísicos, E como ela se aglomera nas galáxias, e a maior parte da matéria na galáxia é proveniente de matéria escura, estima-se que vai ter, então, uma grande quantidade, uma densidade muito grande de matéria escura no centro galáctico. Sendo que ela é não bariônica, então ela não interage de eletromagnetismo, só gravitacionalmente. Mas ela pode interagir consigo. Então, a gente chama esses modelos de self-interacting dark matter, mas também elas podem interagir com alguma partícula padrão, mas isso com uma probabilidade muito, muito, muito pequena, porque o componente é muito, muito pequeno. Então, a ideia é que a gente está recebendo fótons vindo do espaço, vindo dessa direção, por exemplo, do centro galáctico, que é esse excesso que a gente fala. Você está vendo ali, tem uma linha que deveria ser só retinha, só que tem um bumpzinho, tem dois, na verdade, e tem os excessos que a gente fala. E aí, como é que a gente vai explicar esse excesso naquele valor energético ali? Tem uma energia ali, para 2 fótons no estado final que a gente recebe aqui na Terra, que está dando essa energia. Como a gente explica isso? Aí, tipo, como eu falar, tem como usar pulsares. Aqueles pulsares, eles não explicam, eu não sei direito, não vou saber mais, mas eles não explicam muito bem, digamos assim, por alto. Mas sendo que se a gente usa o modelo de matéria escura, ele consegue explicar bem isso. Entretanto, não temos como dizer que isso realmente é uma detecção de matéria escura, de fato, do ponto de vista de detecção direta. E aí, basicamente, o que a gente estava discutindo essas questões com relação a cada canal, que a gente vai conectar os efeitos, que basicamente físico-estatística, que está acontecendo dentro daquele centro galáctico, que vai produzir, microscopicamente falando, né, uma quantidade de partículas, uma quantidade de fótons, que vai ser basicamente um efeito de cascata de interação. Né? A interação aqui gerou uma coisa que a gente observou aqui na Terra. Aí eu tenho que, beleza, são 2 fótons no estado final. Agora vamos fazer o que a gente chama de como é que é? Tipo, track, né? Tipo, você...
como se fosse engenharia reversa.
Uma engenharia reversa, para saber de onde é que veio. O que foi que gerou esses 2 caras com essa quantidade de energia? É alguma coisa que a gente conhece? Joga no modelo padrão. O modelo padrão não tem nada que a gente conhece, que poderia gerar esse processo. Né? E aí, no modelo padrão, não só de física de partículas, mas em modelos de astrofísica, em modelos cosmológicos, em modelos e assim vai. E aí, isso torna-se tipo uma espécie de, não evidência, mas uma forma de, não posso dizer assim, também de sondar a possibilidade de matéria escura. Essa é a viagem.
Isso, e é bem interessante, porque, ao contrário da física de partículas, finalmente a gente chega num laboratório, e aí você cria o sinal que você quer ver, né? Você vai fazendo lá até aparecer alguma coisa. Só que aqui não, a gente não tem controle nenhum sobre o que vem de lá. Então, realmente, é uma análise que ela é bem mais complexa desse ponto de vista, porque você tem que analisar, sei lá, esse fóton que veio, ele pode ter passado por uma região que tenha, sei lá, uma coisa gravitacional muito forte, aí que mudou a frequência desse fóton, por exemplo.
Pode ter também, por exemplo, fusão de fótons. Eles são muito
Não, pode ter alguma coisa com campo magnético muito grande, ou então alguma distribuição de cargas que vai mexer no momento do fóton, por exemplo. Tem tudo isso que pode influenciar.
Apesar do fóton não ter massa, não ter carga, né? Mas quando é uma matéria, aí ele já se comporta diferente. Uhum. E vai sentir também a presença gravitacional. Em modelos gerais assim, de astrofísica intergaláctica, por exemplo, essas coisas já não é nessa área exatamente, mas é a galera que domina essa parte, domina a parte estatística também, que são análises estatísticas. Diz, não, parece que não tem nada aqui não que eu saiba. Vocês, alguma coisa que vocês sabem que pode explicar, o cara não assim, botar um cabinho aqui que não interage com quase ninguém, e isso que foi produzido de tal forma no início do universo, e hoje ele tem uma densidade mais ou menos desse jeito, a gente consegue explicar. E sim, além disso, não só a densidade, mas que está distribuído no universo dessa forma. Né? Que é, no caso, que é esse J-factor lá que ela falou, que é tipo uma quantidade associada à distribuição de matéria escura e o perfil de densidade de matéria escura no objeto astrofísico que você estiver estudando. Isso vai também estar associado com relação a se você está estudando também decaimento ou produção desse cara, produção via decaimento ou produção via interação, espalhamento, alguma coisa assim.
Bom, é isso? Mais alguma pergunta? Pode falar?
So we have the long graph matter, and we suspect it's that matter. So if we look at other regions which are supposed to have a high concentration of dark matter as well, should we see the same problem, the same level?
In principle, yes.
Yeah.
There's that. I mean, there are regions of astrophysical objects such as dwarfs, white dwarfs, which are galaxies that have a low concentration of baryonic matter. However, they are very heavy. So we assume that the concentration of dark matter in this region of these galaxies are higher than in other places. So if we see some kind of signal like this one, it will be a very good evidence in favor of dark matter, for example. Yeah, we haven't seen it. Yeah. No, we're looking for it, but we haven't seen anything yet.
That's the point. That's like there is a plot. It's like I don't remember, but it's like something like this. Probably 50%. Likely.
I'm not hearing very well, so it's,
Yeah, just speak louder.
Here is in the
Let me just change the layout.
Then we have, for example,
Okay.
the probability to have a production of dark matter, say, and also the how strong would be this signal. So here, for example, we're gonna have let's say okay, the probability to measure some signal in terms of galaxy center, for example, it would provide. It is very possible to have an interaction of dark matter, so it would be here, but the signal is not too strong in terms of say, okay, that's dark matter, really dark matter. But in the case of dwarf galaxy, for example, it would be like, okay, it's here. The probability to have the production of dark matter in this place is smaller, but if we measure it, the signal would be very strong. So it's a kind of complementary source.
So I mean, this is not like this.
You mean that the signal is clean? Because in the galaxy center, you have a lot of processes, a lot of background, but as Alvaro said, in the dwarf galaxy, you don't have too much baryonic matter that will, for example, provide a lot of background processes. So you could, for example, in terms of your energy, center of mass, in the number of events, for example, it would be more clean. Let's say the data would be something like this instead of below. See, you could see a better vision about what's going on.
And why would the energy production be
Lower? That's okay. Because since the dwarf galaxy is smaller, you're gonna have a smaller gravitational field, and then the density in terms of, I mean, the density of dark matter, the total density, the large part is dark matter, but in the total, it's small anyway. So the probability to have an interaction of dark matter with baryonic matter, or even a self-interacting dark matter, is small.
Yes, it's just a question of how much matter you have in the same place. Like if you have a galaxy like ours, it's a big galaxy, so it has a lot of matter. But a dwarf galaxy is smaller, so it doesn't have as much. But at the same time, it's good to have do not have as much, because if we see a signal, it will be kind of like a sure signal of dark matter. While in the galactic center, we cannot say that. That's why there this whole discussion of millisecond pulsar, that perhaps you can have a distribution millisecond pulsar that you do not know where they are, but they can produce a signal that is similar to this bump. You know?
Let's say if the same signal, for example, we are observing from the center of the galactic center, it was from a dwarf galaxy, maybe we would say that's dark matter. Then we would probe exactly this energy range here in the Earth, for example, in direct searches or even collide searches.
Yes, that's actually important, because even though we might see, even if we see a signal in a dwarf galaxy, we'll still need to have other ways, detect dark matter in other ways. So it's not enough. So you need like detect like at the collider or by direct detection, something like that.
So the fact that we detect signal from dark galaxies would imply the non-existence of dark matter.
Not necessarily, because we have some experiment, and experiments are limited by their configuration. Perhaps with the region that we can look for with telescopes are not the region that dark matter is. For example, this the sense of energy. We can look for a region of dark matter in that the GeV scale, but perhaps dark matter is heavier, and then we will not be able to see the signal.
And even in this case,
But I understand your point. That's actually very important, because we need to take this seriously as well. If we do not see anything, perhaps it is actually a signal that dark matter doesn't exist. It could be. This could happen.
And speaking specifically about this energy of that moment,
Uh-huh.
so exclude dark matter from this energy.
Yes. That's actually how we work in particle physics. For example, at the LHC, you might look for new particles, and the LHC is sensitive for, I don't know, TV scales. So we haven't seen anything in this scale. So if you have a model that have a particle that should have an interaction, that should be seen at the LHC, and we didn't see nothing, then this region of energy is excluded. So it can only be heavier or lighter, because LHC does not see that. So we're always working in this kind of like how can I say? We are kind of putting the pieces together. You see, well, we look for this region, we didn't see anything. Okay, let's look for other region. Let's look for other, and then we go like that. This is how we do, basically.
the problem is even gravity, modified gravity theories can't explain dark matter, you know. So it's like you don't know.
Yes,
So let's try particle
that's an issue.
physics.
Yeah.
Let's try to use what we know from experiments. Let's try to do what we know from field theory, for example. And let's try to see if we can find something.
Mhm.
But theoretically, it's almost always possible to build a theory that can explain something. But also, it's hard to build an experiment that can search for something specifically, because we have a lot of threshold. I mean, even the experiment that we build will have some threshold energy, for example. So it's like even if I'm not find in such a range, in an energy range, it doesn't mean that thing doesn't exist. They are not just looking in a very specific way. It's like,
Or maybe we're just looking. We're looking.
epistemological
Yeah.
problem.
Yeah.
So we already have the model.
Mhm.
So what we need is a model that can explain the bump. That was
That's the problem, because the bump is not big enough to be a discovery. So we are just saying, well, there is a little bump there that can be explained by anything. I don't know. Could be dark matter, could be this millisecond pulsar, can be at whatever. So it's not, if it was a very big bump, then that would be a very interesting case, because we will have to explain this bump. But it's not yet. So we can only say, well, that's kind of an evidence of dark matter. But you cannot say much more than that.
Yeah, and actually in this paper they do as well a relation with the sigma, that is the significance of the
Yeah.
bump, and they just reach 3 sigma at most, like 2-3 sigma, and it needs to be 5 sigma to be relevant. So
And there's also the issue that this kind of measurement, you have a lot of source of errors. And so this 3 sigma in the sense of a particle physics experiment at Earth would be, I don't know, like 1.5 to sigma. So yeah, it's a very different approach.
Yes.
But very interesting nonetheless. More questions? Let me see. I don't see any questions, so now let's relieve Leticia from this job. So thank you, Leticia.
Bye.
For the
Thank you.
presentation. See you
I
next
will
time.
be able to hear the discussion about the seminars. So bye, but bye.
Okay, but we will decide, whatever we decide, we will put in the group, so don't worry.
Oh, okay. So
No.
bye. Thank you.
Bye, everyone. Talk to